Alrighty. Hello, everybody, and welcome to the live OpenSSL webinar on debugging an OpenSSL application with our very own engineering manager, Neil Horman. My name is Kajal Subkoda, and I will be moderating this webinar. I'm going to go over some housekeeping stuff before we move on to the technical portion of the presentation. As a reminder, all attendees will be in listen-only mode. If you have any questions, please feel free to use the Q&A box or raise your hand to be unmuted if you'd like to ask the question live, as we will host a Q&A session following the presentation. As a side note, if you're experiencing any issues with seeing the full presentation here, please make sure your Zoom is set to the full page setting or check the page zoom level and adjust accordingly. As a reminder, this webinar will also be recorded and be made available on our YouTube channel shortly after the presentation. I invite everyone to follow us on Twitter, as well as YouTube and any of our other social media, which is just at OpenSSL or at OpenSSL_. And feel free to email us at feedback, that's feedback @openssl.org if you have any additional questions. And now I'm going to hand it over to the wonderful Neil for his portion of the presentation.
Thank you, Kajal. I'll skip the housekeeping slides as you've already covered that, and we have a lot of ground to cover today, so I'm just going to jump right in. Thank you, everybody, for joining. I hope you find this useful. So what are we going to do today? We're first and foremost going to admit that software isn't perfect, and that includes OpenSSL. Software evolves quickly, develops a lot, and bugs get introduced. It's part of life. And we're going to discuss ways that you can address issues in your software using various debugging tools. By the end of this presentation, I'm hoping that you'll be able to identify a whole suite of tools available to debug different problem use cases. I'm hoping you'll be able to gain visibility into various problems that are addressed by those tools. And we're going to do a discussion of some best practices to prepare for debugging of in-field issues. Debugging is often generally thought of as a development time practice and operation. In-field debugging is just as critical, and preparation is key to fixing your company's problems there. We're also going to show some examples of how debugging visibility translates into understanding of a root cause of a problem and how to fix an issue. I've made some assumptions in this presentation just to keep you all familiar. In the interest of time, this presentation assumes that the audience is familiar with coding applications in C, that you're familiar with some various high-level cryptography concepts, both in general and regarding the OpenSSL library specifically, and that the audience is familiar with some of these debugging tools being used. If you're not, don't worry. There's lots of reading material out there to get you that experience, so you can always look at this afterwards and come back to it if you need to. So what sort of debugging mechanisms are we talking about? There's a lot to choose from, and this is by no means a complete list, but we have several available to us. Some of them are very tightly integrated and in fact implemented by OpenSSL. These include various APIs like the error reporting API or the trace APIs that we have available. There's also tools that are available that let you debug in general use cases, which you may or may not be familiar with, that OpenSSL has features that you can use to integrate tightly with. Those include runtime and postmortem debuggers like GDB, code sanity checkers like Valgrind and ASAN or Hellgrind and TSAN, and they include other tools that are not directly related necessarily to your application, like Wireshark for network data debugging. And we're going to take a brief look at all of these today. Getting started right away, the error API. This is your first line of defense with OpenSSL. OpenSSL has an error reporting API that implements a per thread stack of errors that get recorded as you make calls into the OpenSSL library. These can be retrieved and printed to the console as your application sees fit. It is effectively the equivalent of printf in OpenSSL. Very handy for identifying functional errors at runtime. Applications, however, don't always present this information because they don't make use of the API. So it's great for development time debugging, and it can be great for in-field debugging after you've released your product, as long as you prepare for it. And that's really what we're going to look at here. Preparing your application to use the error API. OpenSSL, by default, always when built, is set up to raise encountered errors via this API. In order to make use of it, applications should do the following. First and foremost, you should always check the return code of any OpenSSL library calls, because that will give you an indicator that there is something on the error stack to report that you can interrogate. If an API call fails, you can make a subsequent call to a function to fetch those errors and log them. We have a whole suite of them. They're documented at the link below. The most notable is error get error all, which gets you a list of the errors. You can also directly print them to your console with error print errors, or redirect them to a different file pointer with something like error print errors underscore FP. They're all documented, fairly straightforward to use. You should clear errors after every fatal library call. This helps you differentiate errors from one call path from another call path. That is to say, if you never clear your errors, the buffer just wraps and you don't know where those errors necessarily came from. So this lets you keep that clear. And lastly, your application should ideally implement a toggle to enable these in your code or disable them. The idea being that in normal operation, you may not want to see these errors printed, but in a debugging scenario, you may at runtime want to turn them on. And that's a fairly straightforward programming practice. So let's see an example of the error API in work. I've got a sample program here. It's very straightforward. It does nothing useful, but it's good for demonstration purposes. We have a main routine that has a stack variable that is of the EVP cipher type. This is an OpenSSL object representing a cipher. We make a call to EVP cipher fetch, which allocates and initializes this data type according to certain parameters. The most notable one here is the type of algorithm we want to fetch, AES-128 CDD. And we do some error checking. We say, well, if we return null, we print, hey, we didn't get an EVP, and we exit inappropriately or exit with an error. If we did get one, we free and return success. Very straightforward. So let's build and run it. So we run the application and we get no EVP. So from this, we know we didn't fetch the EVP, i.e. it's an error condition, but we really have no idea why. So let's augment that so we can figure it out. Augmenting our example here, I've added one call to the error API, in this case, error print errors underscore FP, providing standard error as the argument file pointer. And this will just print to standard error any errors that the library encountered while we hit this problem. So let's run it again. We got our same no EVP error, but this time we got a lot of extra information that's very helpful for determining what exactly went wrong. This contains several parts. First and foremost, a thread ID can tell you which thread encountered the error. Hexadecimal error code, this is the numerical error code that was raised. It indicates which function this happened in the library, in this case, enter EVP generic fetch. It gave us the error string, which is correlated to the error code. In this case, it said unsupported. It gave us a specific file location. This is where this function is implemented in this specific line that raised this error. And lastly, it gave us ancillary error data. In this case, it said algorithm AES-128 CBV. So this is what this error code had a problem with when trying to execute this function. So now we see we have some information to tell us what went wrong. We know the function EVP or inner EVP generic fetch failed. The error was that the algorithm was unsupported, and the algorithm that we asked for was AES-128 CBV. And if you have some familiarity with the OpenSSL library and cryptographic concepts, we know that AES-128 CBV is not real. It's not actually an algorithm. AES-128 CBC, however, is. So I have a typo in my code. And if we change that, we can see it works properly. Moving along, the trace API. OpenSSL has the ability to do functional tracing of various code paths. This is very useful for diagnosing problems relating to flow through the library, the OpenSSL library. Much like the Error API, this requires some planning ahead for your application, but it does provide a very fast and lightweight way to gain visibility into library runtime behavior. It does need to be enabled at build time, however, as it defaults to off, unlike the Error API, which is always on. So for developers, how do we enable tracing? We have this OSSL trace set callback function that's documented here, and an ancillary OSSL trace set channel function, which allows us to specify where output of this callback goes. Setting a callback for the trace API provides a callback function to use in processing events. Each call to that function contains event data that you can then log to whatever facility you see fit. You need to write that function to log data wherever you like. You can provide a channel to provide a BIO object to redirect that to different locations depending on how fancy you want your application to be. For end users, once you have an application that has written that callback, tracing can be in-field enabled via an environment variable. As an example, you can see this internally implemented via the trace API calls. Again, the library has to be built with enabled trace selected, as it does default to off. And then at runtime, it will still be off unless you set the OpenSSL_trace environment variable. The OpenSSL trace environment variable is documented at the link below and accepts a comma-separated list of event categories that are documented there, which lets you look at different aspects of the library. For an example here, I ran OpenSSL version, which just prints a version number, and selected to trace the init calls. And you can see when I run OpenSSL version, I get a whole series of trace messages here showing functions that are called during the initialization process, after which the heart of OpenSSL version prints, not surprisingly, the version number of the application, followed then by the init messages doing cleanup of the library prior to exit. And there's a whole series of categories available. Without going into too much detail, you can read that man page and see all the different categories that are available to you to debug different aspects of the library without getting inundated with too much data. BIO monitoring. All I/O in OpenSSL, generally speaking, is handled via our BIO or block input-output abstraction. This API covers all sorts of input-output backends, files, TTYs, sockets, just about everything you can imagine that an operating system provides as an I/O mechanism can be abstracted with the BIO API. One of the advantages of that is the BIO abstraction allows for monitoring hooks to be applied to it. This is very useful for tracking localized I/O. For developers, like any other tracing mechanism in OpenSSL, with the exception of the Error API, it requires some level of application preparation. Most notably, it has to be enabled. The application needs to attach a callback to a BIO, i.e. your application has to call BIO set callback EX, to which you pass a BIO object, which is the input-output object you're using, plus a function that gets called back when anything is read from or written to that BIO. You can see the function prototype of that registration function here. The callback then is called and receives the BIO operation and any data sent or received on that object, to which you can log any way you see fit. For users, if application developers provide an option to enable BIO monitoring, you can provide low-level internal details of data input and output to the application. A great example of this is the OpenSSL S-Client applet, which has the -debug option. -debug is the runtime enablement switch that tells the S-Client applet to register a BIO hook and print anything read to or written from the S-Client's SSL object to the console. This lets you see the hexadecimal dump of any data we're sending to a server with this applet. So here's an example of it in action. We run OpenSSL S client with the debug option, and we connect to localhost port 22. And you can see here that we get a whole bunch of data input and output to it. It is not particularly useful without context around it, but if you're trying to debug low-level I/O issues, maybe I/O interleaving or what have you, this gives you great visibility into that. Moving ahead again, the trace API. This is separate from our functional trace API. I'm sorry, I should call this the SSL trace API specifically. Unlike the trace API, which we just covered, this trace API allows insight into SSL and TLS records as they are sent and received. So unlike the functional trace API, which just tells you what functions you're calling, this will tell you, oh, you sent an alert message, or you received a handshake server hello record, so on and so forth. Great for sort of mid-level debugging of TLS connections between a client and the server. It does need to be enabled again when you configure OpenSSL. You need to turn on the enable SSL trace option, otherwise it will default to off. So that is
sorry, Neil, I'm just going to correct you there. It actually defaults to 1.
It does default to on.
It does. It used to default to off, but we changed it several versions ago.
Oh, I'm sorry. I wonder if I was looking at an old version. Thank you. Good to know. So you heard it here first. SSL trace enable SSL trace defaults to on. You can disable it, however. I would not recommend it. It does, however, still require application setup to use. One note, and this is a topic for which we should not dive too deeply on here because we'll talk about it all afternoon. Windows users need to build their application with the app link bindings to enable the proper runtime settings to make this work. And the whole description is available at the link below. So for developers, above and beyond enabling or selecting the default for using the trace API, the SSL trace API, your application needs to make a call to SSL set message callback. This API accepts a pointer to your SSL object to trace, as well as a callback function. Not surprisingly, you can also set a message callback arg, which allows you to pass application-specific data every time that callback is invoked. Once that's done, on record send or receive, the callback is invoked, passing the content type of the record, i.e. alert, change cipher, in the whole suite of TLS messages or TLS record types that are available, as well as the application data and the contents of the record. Your callback is then free to decode and log as needed. We have a existing callback function called SSL trace that is available for application use that does a lot of this for you in sort of a, if not standardized, at least common format that you can take a look at or just use in your application as needed. There's a convenience. For end users, you need to enable this at runtime. Generally speaking, an application much like the Error API or what have you would need to enable a toggle to turn this on. The OpenSSL S-Client applet, again, implements record tracing with such a toggle known as the trace option. This will cause record information to be presented in the console as exchanges with the server occur. So, a quick example. I have an environment where I've run an OpenSSL S server. I've explicitly and purposely set it up to only accept TLS1 records. And I'm running a client, which I've set the trace option on and told it to connect to localhost where this S server is running. And you can see here when I connect, this is truncated for size. I apologize, I did not want to give you an eye chart. But you can see here an example of the sort of things that get printed to the console. It'll tell you the client sent a TLS record. It'll give you the version, the content type. So this is a handshake method. It'll tell you the client version, in this case, TLS 1.2, and all the other things that come with a handshake record. And then you can see we receive a handshake, excuse me, not a handshake, a TLS record from the server. The record type is an alert type. Specifically, it says we have a protocol version error and then it's fatal. This is expected here because we specifically set up the server to accept TLS 1.0 only, and we sent a 1.2 client hello. And so it said, nope, you can't do that. Sort of a simple and trivial example, but it shows you how you might be able to debug TLS connection issues between a client and server easily without having to set up a whole lot of other harness here to capture this sort of data and decode it. Let's step back for a bit here. We talked a lot about various mechanisms that are built into OpenSSL to do debugging, but of course that's only a very brief or small facet of what you can use to debug applications with or without OpenSSL. GDB is a big one. I don't want to talk here a whole lot about how to use GDB. That is a dozen webinars in and of itself. I also assume that most people have some familiarity with using a runtime debugger, how to do back traces, variable inspection, what have you. What I would like to do, however, is talk about how to use GDB more. Many applications enable debugging info using their compiler's -G option to produce dwarf data, which is what GDB uses to understand how a program is assembled and laid out when it's used to debug a program at runtime. However, it's been my observation that for production builds, when you actually ship your product, that dwarf building is disabled to save space in the binary. Dwarf information is large. You can easily double your application size by including it. And so a lot of production builds turn it off because space. However, that's bad because it leads to a lack of visibility for in-field debugging. Some of you may have had this experience before. You ship a product and a customer encounters a crash that you didn't catch during your testing phase, and they send you a core dump saying your application crashed. And you get it, but you can't do anything with it because the application that crashed didn't have any dwarf info built into it, so you can't disassemble it and figure out what's going on. That's bad, and it's a bad look for a company because it requires customers, if you do want to diagnose the problem, potentially to install a debug-enabled build and then reproducing the problem, which might be difficult in their environment. And so it's just not efficient. Wouldn't it be nice, however, if you could ship non-debug builds but still analyze a core dump when they occur? We can absolutely do that, and that's kind of what I'd like to talk about here. As mentioned, debug builds add dwarf information to a binary, which is good, lets you debug. Bad, increases size. GCC and CLang offer the ability to separate out dwarf information, however, from the rest of your binary into a separate file, linking them together for the purpose of later debugging. You may have seen this in some distributions in the past, or currently rather. Distributions like Red Hat or Ubuntu or Arch will often include repositories that are debug info libraries. What they're doing there is exactly what we're talking about here. You can do this for any ELF file, and OpenSSL contains a mechanism now very recently added to allow you to do this separation of dwarf information from production build data. The target is make debug info. That works reasonably well. And it does the following things here. I know this is a bit of an eye chart, but this is sort of a breakdown of how to do this for a libcrypto or your OpenSSL libraries or any library or application in general. What you want to do is you want to take your shared library, in this case libcrypto, you want to build it with dwarf information included, and you want to move that out of the way to some temporary file name. We'll restore it in a minute. Next, you want to strip everything from the full build to a copy called stripped. This removes any non-exported symbol from your symbol table. OpenSSL already does this, but it's here for completeness because you may have other libraries that don't do this, and it's a space-saving feature. Next, we're going to make a copy. We're going to use the object copy tool. We're going to tell it we only want to keep the debug info, that is the dwarf section of your ELF file. We want to use the full version as our source input and a .debug version as our output. So after this step, we'll have this library, libcrypto.so.3.debug, which is only the dwarf debugging information. Lastly, we're going to make another copy. And this time, instead of only keeping the dwarf info, we're going to get rid of the debug info. Additionally, we're going to add an ELF section into the file called GNU debug link. What this does is it tells GDB and several other debuggers, if you're analyzing a core dump or this application and you need dwarf information, you're not going to find it here. You're actually going to find it in this file. And we're going to take the full copy here, and our output is going to be the original file name, except it's not going to have dwarf info in it anymore, just this link to say, go find it here. This is what the make debug info target in OpenSSL does, and it produces for you a set of dynamic shared objects that you can use as a production build to ship, plus this debug information that you can set in an archive locally. So if you have a customer in the future that says, hey, your application crashed, you can immediately start debugging that crash without having to rebuild with debug enabled and ship it to them and get them to reproduce. Very handy time-saving feature. I don't see a lot of this going on outside of distributions. I wanted to put it in front of you here because this is a fantastic preparatory step for being able to debug OpenSSL and, in fact, any other library or application in the field. So that's a big list, and the list just keeps going. So in the interest of time, I just wanted to summarize a few other debugging tools you might have available for you here. All of these work fairly well with applications that integrate with OpenSSL. There's the strace tool. Many of you are probably familiar with this one. Very handy for tracing system calls into the OS. If you have IO hangs or what have you, this is a great way to find them. SOCSTAT or LSOF identifies open file descriptors for an application. Great if you happen to be leaking file descriptors or encounter errors of that nature. Difficult otherwise to gain visibility with tools like GDB on things like that, and LSOF is there for you. LD debug is an underutilized one that a lot of people don't know about. This is a glibc environment variable that is used to trace dynamic library loading. If you set it to 1, I think is the setting, you can see what order and what order libraries are loaded in by your application and where symbols resolve to. If you have multiple high stack depth of library loading, i.e. if you're loading OpenSSL that loads an engine that loads a private copy of OpenSSL, this is a great way to see the order things are happening in. If you get weird symbol resolution bugs, this guy's your friend. gprof and perf are great for statistical gathering of performance data. gprof allows instrumentation of your binary to gather function call counts and code path execution so that you can determine where your application is spending a lot of its time. Perf similarly will do that, but uses hardware event counting, for which there are a number of counters. You can detect cache miss rates and branch miss rates with perf. Very, very useful if you get a chance. System tap is one that's very near and dear to my heart that gets ignored a lot, I'm afraid, but is super useful. I had a whole example here, but I cut it for time. It is a programmable debugger. It not only allows you to do a lot of the things that GDB does, but allows you to dynamically enhance the functionality of things like OpenSSL at runtime. Verbally, I'll give you an example. I had a request from a user that said, I want stack traces every time the error API adds an error to a thread stack. Well, adding that in the code is a lot of work for just a narrow debugging use case. However, with System Tap, you can add that in with a script. Very useful. Used to only do kernel, or used to only be useful with the kernel. In recent years, it is now very useful with user space applications. I strongly encourage you all to take a look at that. It's incredibly powerful. So lots of reading homework there. Moving on, behavioral problems. Not all problems are crashes. Some are just behavioral issues that are suboptimal. Sometimes they lead to crashes, sometimes they don't. These are things like memory leaks, right? You run your application for a long time, and all of a sudden you're using 47 gigs of memory. And if your program is a simple web server, that seems wrong. Or you might have undefined behavior in the language. Weird overflows when you didn't expect overflows or things of that nature, or just simple thread race conditions, right? The variable that you knew was a certain value just a second ago magically changed and nobody changed it that you could see. We have tools to address this sort of stuff. Address sanitation in the form of Valgrind and ASAN. These let you find memory leaks, double freeze, invalid accesses, etc. They're available in multiple technologies, most notably dynamic binary instrumentation. This is what Valgrind does. It dynamically hooks into your code at runtime and runs your application as a child process, monitoring certain key function calls to detect these sort of errors. Or we have compile time instrumentation, which is the libasan or -f sanitize equals address parameter to your compiler. These build instrumentation directly into your library and have support libraries to use those instrumented hooks. OpenSSL, of course, supports both of these. Particularly the compile time instrumentation can be built in by configuring with the enable -asan option at build time. Quick comparison, ASAN and Valgrind obviously offer very similar functionality, different technologies to get there that offer you different performance advantages and disadvantages. Most notably, compile time instrumentation via ASAN is going to be relatively much faster than Valgrind. Dynamic instrumentation tends to slow things down quite a lot, though advantageously for Valgrind, running your application can be done at will without having to modify your application. So that is very useful for in-field debugging. Both cover generally the same feature set. Valgrind tends to lag a little bit behind compile time instrumentation, but it is catching up rapidly. I encourage you to go read and investigate which one might be useful to you. You'll generally find both are useful depending on your exact use case. Here's a quick example of Valgrind. This is our example from the Error API example. Said that weird. It's got one minor change. I'll see if you can guess what it is. When running this application, we see that after it runs, Valgrind outputs a error summary. It tells us we leaked. We lost 248 bytes directly, and indirectly we lost another 603 bytes. Well, that's bad. But where? Well, Valgrind tells us that we can rerun this with the leak check equals full option. This provides us with a call stack showing where we allocated the memory that we never freed. And you can see here from the bottom of the stack that EVP cipher fetch was called, and we allocated a whole bunch of memory down here, and then we never freed it. And if you look back at the example, you can see I just removed the call to EVP cipher free. Valgrind will show you when you do things like that. This is, of course, a trivial example. As you all know, your applications are going to be much more complex, and this is a great tool to get visibility on those corner case errors. Also a great tool to run regularly in your CI, either via Valgrind or with libasan enabled to catch those sorts of errors before you ship. So Valgrind, oh, had an extra slide in there. Oh yes, you can see here after I restored the call to EVP cipher free, we now report there's no memory leaked at the exit at the termination of our application. Hellgrind and TSAN. These are to thread sanity what Valgrind and ASAN are to memory safety. Most modern compilers come with the ability to detect thread errors. They can be enabled on the command line with -f sanitize equals threads. This can be passed directly to the OpenSSL configure script, and we can do compile time enabling of thread sanity. So OpenSSL can build with that on. And like Valgrind and ASAN, these are different technologies to provide similar functionalities, each with their own advantage and disadvantage. Hellgrind is a sub-tool of the Valgrind suite. It does dynamic binary modification, and as such tends to be relatively slower than its compile time instrumentation counterpart, that is libtsan, which can be enabled with the -f sanitize threads option. Both are functionally equivalent in terms of their feature set. They just discover read after write, write after write, and write after read races, as well as deadlock and lock inversion issues. Here's a quick example. Similar to our previous example, except in this case, I'm creating two threads, both of which run the do EVP function, each of which fetches a cipher and frees it. Noting here, I have a global variable for EVP. Running this, it gives us an output report saying, hey, we have a data race. thread 3 wrote 8 bytes at this location, while this thread number 2 also wrote 8 bytes at this location without any locks in between. I noted the global variable EVP. This arises because we have 2 threads that are both writing to shared global data. That is, of course, a no-no without any sort of synchronization in between. So Hellgrind here was just noting the fact that I have 2 threads that are accessing the same area of memory without creating any locking between them to ensure that the writes happen in an appropriate order. Home stretch, network problems. Cryptography doesn't generally exist in isolation. Most typically, you're writing an application to do something useful for your customer base, and OpenSSL, while a fantastic product, is really just a component in all of your software that's used to create TLS connections for which you can ship your sensitive data between your client and server back and forth without having to worry about eavesdropping or man-in-the-middle attacks or what have you. This creates sort of a strange problem, though, because it makes data exchange very secure, but it also makes it very difficult to diagnose networking problems. That is to say, if you have a client and a server that are exchanging data and something about that data is not quite right, you may want to look at it as it's in transit over the network, but you can't do that because TLS encrypts it, so it looks like gobbledygook. That's inconvenient. So we need a way to be able to see application data within a TLS encrypted exchange. And here's just a visual representation of that in Wireshark. I set up a client and server. I apologize for the eye chart here. And sent the message, hello, over the network. And I wanted to look at the network data and make sure that the word hello was actually getting sent. But as you can see here, the application data in this TLS exchange is illegible, as it should be if TLS is doing its job properly. So undecoded TCP dumps are largely useless, but we can decode them. OpenSSL features a key logging callback. This is a standardized file format codified in this IETF draft document, which you can find linked below. It lets us make use of the SSL CTX set keylog callback function. The callback is fairly straightforward. It provides a function callback to invoke, and every time an SSL or TLS message with a key exchange happens, that callback is invoked, and you can log the key using this command, or this function rather. This is command line implemented in our S client with the keylog file option. Also, I'll call an audible here. We currently have under review a option to allow the use of the SSL keylog environment variable, which is, if not standard, at least a common method for implementing keylogging callback without the need to enhance your application to do so specifically. So eventually, probably in the 3.5 timeframe, you won't need to use SSL CTX set keylog callback at all. You can just set an environment variable if you have that feature enabled in OpenSSL, and it will just magically work, producing a key file that can then be read into tools like Wireshark to decode your TLS session in your TCP dump file. Fairly straightforward to use. It's a little bit difficult to show you here, but there is an option under your protocol preferences in Wireshark to input that keylogging file. And you can see when you input the file, it decodes my message. Hello. So makes it very easy to debug networking problems while still using TLS without having to use anything temporary to do debugging while you're doing that. Closing thoughts. I spoke very fast here today. I apologize. We had a lot of ground to cover. We didn't even really have time to get to performance issues. But the things I'd like you to take away today are that OpenSSL offers support and utility for a wide variety of tools. Some of them built right in and very specific to OpenSSL, some very generic that we strive to work well with to make your debugging life easier. I encourage you all to make very liberal use of them. My favorite saying when debugging is visibility is the key to understanding. You can't fix a problem if you can't see it. And so these tools will help you immensely. They will help you both in your development environment, and they will help you in your in-field deployments if you prepare. Preparation is a debugger's friend. Build your libraries and apps with debugging in mind. You will save time in the end. And lastly, there's far more tools here than what's been discussed. These are just the highlights. I would encourage you all communicate, use our discussion boards and our other community resources to figure out how to debug problems. Debugging is as much of an art as a science, and asking a question for how to debug your situation may yield somebody that says, I had that problem too, and here's how I solved it. And that's how we all learn. Yes, somebody may have a tool or approach you haven't thought of. And that's a wrap. Who's got questions?
Alrighty, we have a couple of questions here. First one being, is there a way to trace provider selection? For example, what were the reasons why a specific provider's decoder was chosen?
That is an excellent question. I am going to immediately admit that I don't know the answer and ask Matt or Tomasz if they might contribute there.
Unfortunately, the answer is no. There are quite a large number of trace categories that we have, but provider selection isn't one of them, I'm afraid. That would be a great thing to add.
I was going to say, that is a great note.
Yeah, let's remember that one and create a feature request for that, because I think that would be very useful.
I agree.
I would add that there is a trace category for decoders, for decoding, and the decoding API. So there is a lot you can see by this trace category, but not sure if it would be like sufficient for you. It's at least it's worth trying.
Does Tomasz, just to follow up, does decoding tracing imply provider lookups?
It shows which providers, which decoders from which providers were called. It does not show you probably like the fetching or how the selection of the implementation from which provider.
Right, and of course it's decoder specific. So
if this is decoder specific.
Yeah, if you're fetching ciphers, then that doesn't really help. So it's a useful tool for that specific case.
Well, I feel like this is a win here. We've walked away with something we can work on. Thank you.
Awesome. We have another question here. Any tips and tricks with these tools, debugging leaks, memory problems in the FIPS provider?
As long as there are no follow-up questions, sure. I think so. I'll say first, debugging the FIPS provider should be no different than debugging any other provider. So the fact that you're asking about FIPS should be invariant to any other method that you might follow. I think the big challenge in debugging any provider is the fact that, generally speaking, Matt, Tomasz, keep me honest here, is that we load them using the DL open call. And so tools like GDB may have a hiccup during symbol resolution, though I think
it should be okay in most cases, but the FIPS provider is a bit of a gotcha, actually, because the FIPS provider, a lot of the symbols in the provider are duplicates of ones in the main libcrypto library. So that can be quite confusing if you're looking at stack traces and so on, because you'll suddenly see symbols that are specific to the FIPS provider, but actually duplicates of ones in libcrypto, and you're not quite sure which one you're in. So you just have to be a bit careful.
That's a good point.
Yeah, there is also one handy feature in the 3.4 version that will be released soon, that you can disable on build time. You can disable the FIPS provider self-tests on startup. So that's handy because in the debugger, when you put a breakpoint on some crypto function in the FIPS provider, it will like the breakpoint will trigger during the load of the provider, and usually not at the time when you actually are you want to see your actual call. Yeah, so it will first trigger during the startup of the provider. If you, for example, you want to trace signing or whatever other crypto operation.
Okay. I will add, Matt jogged my memory on this, that as you mentioned, GDB gets a little wonky regarding symbol resolution because of the symbol duplication in the FIPS library. This is an area where, and I feel bad that we didn't talk more about this, SystemTap in fact shines, specifically because SystemTap has a model in which you probe specific functions, and the specification of those functions is at a granularity such that you can define specifically which library that symbol occurs in. So I'd strongly encourage you here to look at SystemTap if you're looking at the FIPS provider significantly. That may well help you.
Norman, who asked the question, would like to, I guess, has a follow-up live.
Yeah, thank you. Yeah, so you guys hit it on the head, especially with the self-test. So part of the question was around, the ability to disable self-test or to even debug self-test in some of these scenarios. But it sounds like you're saying, once you get beyond self-test or the ability to disable self-test, that might be a help. And what I was getting at specifically was, I wasn't sure the integrity hash, is it embedded in, it gets embedded in the FIPS provider? And so at the time of integrity check, it's checking that .cnf file.
Well, the integrity hash is in the config file. So unlike if you've used like the old FIPS provider, the 2.0 module, the hash was embedded sort of within the file itself. But that's not true with the sort of the 3.x FIPS provider. It just loads the hash from the config file, and it hashes the DLL or .so or whatever, and compares the two and checks that they match.
Okay, thanks. I know it's not appropriate here, but I'll just throw in, just yesterday we came across this issue with Red Hat where the very tool mentioned, the strip tool, was causing us problems where it stripped the symbols. We just noticed that the size of the .so was like significantly smaller than when we built it, than when we installed it on Red Hat. And it was because it seemed like the symbols were removed, and so we failed the integrity test because of that. But I know it's not appropriate to discuss that here.
That's actually interesting. Yeah, I would not have thought stripping the symbol names would have affected that, but in thinking about it, I'm not quite sure what else sections we compute our integrity check over.
We do the check again, like across the whole SO, the shard library.
So at the file level, we don't extract specific.
Yeah, we don't check the sections, anything. We don't parse them.
I think someone from Red Hat would like to respond, actually.
Correct. Yes, the integrity check works different on Red Hat-based distributions, so what's being said here might not apply to this particular situation.
Thank you. It's Red Hat's fault.
Yeah.
Correct.
Sorry.
That's if you are using the Red Hat's patched OpenSSL, but if you are using, of course, the upstream one, then.
But good.
So,
We all learned something today. That's good
yeah.
to know.
Yeah, awesome. Thank you guys so much. Thank you, Norman and Clemens, for speaking. We have some other questions here as well. Is there a recommended way to cache algorithm fetches to optimize applications?
Tomasz, Matt, you want to handle that or shall I?
I'm not so sure there's a recommended way. There is actually, we have had previous webinars on some of this.
The previous webinar was talking about this actually.
Yeah.
Yes. So if you head over to our YouTube channel and have a look at some of the previous videos, you'll find some material on that.
Awesome. Our next question here is, are there any gotchas with the debugging when running a 3.0.x FIPS provider with a later version, say 3.1.x?
I don't think above and beyond the gotchas that we talked about with generally debugging the FIPS DSO. Matt, Tomasz, can you think of any others? None immediately spring to my mind.
Yeah, well, again, I'll go back to the thing I said previously where you can get the same symbol appears in both. And so that can be quite confusing, especially if it's from different versions of OpenSSL. But yeah, otherwise, I can't think of a major issue with that. Unless
No.
Thomas has anything to add.
Sounds like no. Yeah, I just say, again, if the symbol resolution gives you trouble, system tap might be a great alternative for you there.
Awesome. Okay, our next question here is it possible to use OpenSSL libraries on kernel side area for data decryption / encryption especially for TLS packets handling networking, because they need to handle data efficiently on the KTLS side?
Not sure how to answer that question. I was going to say the kernel implements KTLS, but you included that in your question, so I'm not quite sure how to respond to that.
Yeah, I'm not quite sure if you're asking whether KTLS is supported, in which case the answer is yes. You can use libSSL and have it offload the KTLS aspects to the kernel. So that's all possible.
If the question is about like whether kernel can use OpenSSL, well, no, OpenSSL is user space library. I don't think it can be like loaded in
not
the
a lot
kernel.
of advantage to making that callback. I mean, your performance would stink. Yeah, I think if that's the question, there's no trampoline back into user space for using KTLS with OpenSSL.
Okay. Awesome. Our final, I don't know if this is a question, more of a comment. iTrace might be a good addition to the other tools list. It's a great way to see library. It's called, sorry?
Ltrace.
Yeah.
Oh, sorry, Ltrace.
Yes, I should have included that. Thank you. Go on. I'm sorry, Kajal.
Might be a great way to see library calls an application makes to OpenSSL.
It is, in fact, a great tool to use. It is a little bit unperformant, and I've never quite figured out why, but it is great if you're not interested in system calls, but are interested in library entry and exit.
And this was a question we answered through chat, but it might be good to just reiterate the answer live here. Is there a default implementation of a trace callback available in OpenSSL that prints useful human readable output to stderr, so I don't have to re-implement that in every application I might want to trace?
Yeah, so I'll just sort of reiterate my answer that I did in the chat there. So no, we don't actually have a sort of standard one that you can just pick up and use, but there is one. Well, at least not in the library, but there is one in the app, so you can at least look at the code and use it as a starting point for whatever callback you might want to write.
Matt, was this for BIO tracing or?
No, I think I think the question was about the trace API.
Oh, okay. Yeah, like you said, there's an example in the OpenSSL app space that shows how to do that.
If we're talking about SSL trace, by the way, then there is a standard callback,
Yeah.
which is called SSL_trace.
Okay.
So you can just use that.
Awesome. Alrighty, those were the last of our questions. Thank you, Neil, for a wonderful presentation. And thank you, Matt, Tomas, Hannah, and Sasha for all attending as panelists. Thank you, everybody, for attending our webinars. Some final housekeeping stuff. This webinar is being recorded and will be made available on our YouTube channel shortly after this presentation. I will be sending up a follow-up email around 5 days after this presentation with links to both the YouTube video as well as the slide deck. And as always, if you have any questions or comments, please feel free to email us at any of our emails, but at feedback, that's FEEDBACK at openssl.org. We will be fielding that the most. Again, thank you so much, and I hope everyone has a fantastic rest of their day.
Thank you, Kajal. Thank you for attending, everybody.